Okay, so in this video we're going to keep going with chapter 9. We're going to start out by looking over these problems that we had finished with last time. So hopefully you got a chance to try those out on your own. Okay, so just to remind yourself, we need two numbers that multiply to this last number and add up to the middle number. So I need two numbers that multiply to negative 20 and add up to negative 8. Negative 20 tells us we're going to have, again, different signs. I'm going to just think about factors of 20 first, and then I'll deal with the negative. So 1 and 20, 2 and 10, 3 does not go into it, 4 and 5. Now I know it's going to be negative, so I know one of those has to be negative in each pair, and this means I have to have more negatives. Okay, so the bigger number in each case is going to become my negative. And if I check, this middle grouping is the one that adds up to negative 8. So I end up with x plus 2 and x minus 10. Again, with these, I suggest that you always check them by multiplying back. We're not going to do it right here to write it out, but you can even see x, that's going to be x squared, minus 10 plus 2 is negative 8. 2 times negative 10 is negative 20. Okay, number 3. I need two numbers that multiply to negative 24, add up to 5. So you may be, as you're doing more of these, you might be getting a little more familiar or comfortable, I should say, with the sign rules. So again, this means different signs. This means there are more positives. When I'm adding two numbers with different signs, I'm really looking for the difference. So really what I'm looking for here is two numbers that multiply to 24 and are 5 apart. Okay, if I think about 24, 1 and 24, 2 and 12, 3 and 8, 4 and 6, more positives, so to make it negative, the smaller number in each case is going to be negative. Here are my 2, so I get x minus 3 or x plus 8. Again, you can have it the other order, x plus 8 times x minus 3, as long as your 8 is the positive one and your 3 is the negative one. And finally here, we're looking for two numbers that multiply to negative 24 again. Again, they're going to add to a positive. This time they're adding to a positive 10. So notice that I'm looking at the same set of factors here, okay? But this time I'm going to use negative 2 and 12. So this is where you really want to check, and this is, as I was saying the other day, where that middle term is going to come into play, because in both of these, let me just do this here, minus 2 and x plus 12. For both of these, your first term is going to be x squared, and your last term is going to be negative 24. It's just a matter of that middle term being different. Okay, number 5 looks very similar, except I'm multiplying to a positive 24 now and adding to 10. So this is where these little subtleties come in. If it were still a negative 24 and it were a negative 10, then I would be at 2 and negative 12, right? It would just be switching the signs. But this is a positive 24. So this means the signs are going to be the same. And since they're adding up to a positive 10, it means they're both going to be positive. So if I think of 24, now this time I have the same number parts, the same absolute values, but I have all positive this time. So now 2 and 12 had a difference of 10, so that worked when the signs were different. But now I want two that add up to 10 when the signs are the same, so I'm going to have 4 and 6. Again, when you check it by multiplying, you'll get what you started out with. Okay, number 6. So this one we would need two numbers that multiply to 12 and add up to 10. Both same signs, both positive, right? So same signs, both positive. Okay, so I think about factors of 12. 1 and 12, 2 and 6, 3 and 4. So I'm looking for two that add up to 10. Okay, well these add up to 13. Let's put an arrow here. These two add up to 8. These two add up to 7. Okay, I have all the factors of 12, both positive, and there's nothing that adds up to 10. So we say that this one is not factorable, okay, because there is not a pair of factors of 12 that add up to 10. Okay, it doesn't exist. We call this prime. So think about a prime number, like the number 3. The only way to make 3 is 1 times 3. There's no other pair of factors. And same idea here. The only way to factor this would be 1 times itself, right? You can't break it up at all. Now, my one concern with when I teach about prime is that this is why I wrote this out, this like reason for why we know it's prime, right? We've looked at all the factors, pairs of factors of 12. We've checked that none of them add up to 10. So my concern is sometimes people think as soon as like I can't find the answer, it must be prime, right? Well, sometimes it just takes a little bit to go through the problem. So I don't want you to think as soon as you can't find an answer, think it's prime. I want you to know why it's prime. That will keep you from making the mistake of saying something's prime when it's not. If you've checked all of them, like we've checked all the factors of 12 and we've checked what they add up to, we kind of have some proof to our claim now. Okay, now the important thing, we had talked about this before, is to always look for a GCF first. And we hadn't really done that in the other ones in this set, just because I wanted to get you used to doing this. But if I look back, none of these had a GCF other than 1. And the reason I can say that easily is because they all have a 1 in front of the x squared, so I can't take any number out other than 1. And none of them have an x in the last term, so I can't take an x out. Okay, so these did not have a GCF, but we always want to look for a GCF first. So if I look at this problem, when I first look at it, it does not look like one of these easier trinomials because it has a number in front of my x squared. But sometimes that can be deceiving. So you want to always look for a GCF first, and then whatever's left will sometimes kind of fall into a different category than you thought. So in this case, my GCF is going to be just 3. If I look at this, 3 goes into each of those numbers. It's the biggest factor I can pull out. And x is not in all the terms, so I can't take out an x. So my GCF is just 3. So think back to GCF. I factor that out or divide it out. Okay, so I did this kind of fast, but these are pretty simple, right? So 3x squared, I take out the 3, I just have x squared. 18 divided by 3 is 6, I didn't touch the x. 24 divided by 3 is 8. So I have this. Now, when we were just looking for GCF, maybe we were done after we pulled it out, but now we have to keep going. What I have in my parentheses here is this easier trinomial. So now I can go ahead and factor that, remembering that I need to multiply to positive 8 and add up to 6. That may be one you can do in your head, or if you think about factors of 8, they're both the same sign, both positive. It's going to be 2 and 4. So x plus 2 and x plus 4. This is in fully factored form. So it didn't look like an easier trinomial at first. Once I pulled that GCF out, it kind of transformed down, it got simpler, and then I could. You have to keep that 3 with it, because remember, whatever I have at the end has to multiply back to give us our original problem. And I need that 3 to get back to that original polynomial. The other thing I wanted to mention is that when you're checking this, you can just do 2 at a time. That's how we multiply more than 2 terms. We have to multiply 2 at a time. So if I have 3 times x plus 2, I get 3x plus 6, and then I would multiply that times x plus 4. So 3x times x is 3x squared plus 12x plus 6x plus 24, right? The 6x is here, the 24 is there. It's 12x plus 6x do give us back that 18x, so it checks. You also could have multiplied the 2 binomials first and then multiplied the answer to that by that 3. Okay, next one, 8. 5x cubed minus 20x squared plus 15x. This really doesn't look like the kind we've been doing, okay? And sometimes, when you have a number in front of here, it won't be the kind we're doing. We'll get to those in a minute. But we always want to pull out a GCF, and sometimes we're surprised by what's hidden in there. Okay, so my GCF here, I can take out a 5 out of each of those, and I can also take out an x. So my GCF is 5x. So I'm going to pull that out here. If it helps, you can write these out as division. So 5x to the third divided by 5x. X to the third over x to the first is x squared. Minus 20x squared over 5x is minus 4x, right? 2 minus 1 is 1. and 15x over 5x, the x's are going to cancel out. I'm just going to get 3. So in these parentheses, I have x squared plus 4x, or sorry, minus 4x plus 3. It's always a good idea at this point, even off to the side or just in your head, to multiply it back, to distribute, to make sure that you haven't made a mistake at this point. Because if you have, you can't go on, right? So 5x times x squared is 5x to the third. 5x times negative 4x is negative 20x squared. 5x times 3 is 15x. We're good there. Now I look at what's in the parentheses and I think about if it's something I know how to work with. In this case it is. It's an easier trinomial, so I'm going to see if it's factorable. So I need two numbers that multiply to 3. Okay, so that's a good sign, right? When this number is prime, that makes our job a lot easier because there's only, it cuts down on the possibilities. So if I'm taking 3, I can only have 1 and 3. Now I look at this and this tells me they have the same signs. This tells me they're both negative. So I'm going to have -1 and -3. Those do add up to -4, so that's exactly what I was looking for. So x minus 1, x minus 3, again, multiply all 3 of them back to check it. All right, so we'll talk about this more in a few minutes also, or maybe in the next video, but always look for a GCF first, okay? Because you might start out with something that looks one way or looks really tricky, and once you pull that GCF out, what's left is relatively simple then and kind of heads you down the path. So when you first look at a problem, you don't necessarily need to know all the steps you're going to take. All you do is do one step at a time. So first you look for a GCF. If it has one, pull out the GCF, and then you can evaluate what you have here, analyze it for what you can do next. And I'll have that all written out in a minute too. Okay, so let's go on. The next type of factoring that we can do is the difference of perfect squares. So this is has a lot of vocabulary words in it, right? So let's kind of break it down. We're factoring, we know that. The difference means to subtract. And perfect squares, we know what perfect squares are, right? We talked about those in chapter 7. So they're numbers whose square root is an integer. So it's numbers like 25 and 49 and 4. So we want to know what these look like so we can identify them. Okay, so let's first put that thought aside for a second. Let's start out by reviewing, like we have been, by multiplying two things. So I have two binomials here, x plus 3 and x minus 3. And I'm going to start out by multiplying these. So x times x is x squared minus 3x plus 3x. 3 times -3 is -9. Now I'm going to combine like terms. So x squared, I combine these two, they actually cancel out. -3x plus 3x, so I have -9. Okay, so this is my answer when I multiply these two binomials, which is a little bit unusual because usually these two middle terms combine and I would have some middle term, x squared plus 5x or minus 13x or whatever it is. So it's a little unusual that I multiplied these two and ended up with a binomial. This is a situation that is the difference of perfect squares. Okay, it's the difference because it's being subtracted. Two things are being subtracted, x squared minus 9. And the two things being subtracted are both perfect squares. X squared is a perfect square because x times x is x squared. So we know that if it's a number, this is true. Or remember, if it's not a number, if it's an exponent, then it means that the exponent is divisible by the index. In this case, 2, if we're talking about squares. Okay, so in essence, I need to look for an even exponent here. If it has an even exponent, then it's a perfect square. Okay, So those are both perfect squares because x times x equals x squared and 3 times 3 equals 9. So again, our job when we're factoring is to start out here and know that I need to factor it back to something that looks like this. Okay, so the trick, our little detective trick, is to say, okay, if it's the difference of perfect squares, if that's the format, then I am going to go back and factor it into two binomials, and they're always going to be like this: x plus a number times x minus a number. Okay, that way the minus number x and the plus number x are always going to cancel out. X times x, or whatever this first term is going to be a perfect square because it's something times itself, and so are the numbers. Okay, now the first term might be a little bit more complicated than just x. We'll see that in a minute. All right, so let's put this all together. We look at number 9. We're asked to factor this. It's x squared minus 100. So first thing I'm going to do is look for a GCF. Okay, there is no GCF. The only numbers that go into one here is 1. So the only numbers they have in common, the factor is 1, which doesn't help us. I can't take an x out of this last term because it doesn't have one. So I do not have a GCF. So now I look and say, okay, I have something with two terms. Is it the difference of perfect squares? Well, it's a subtraction, and both of these are perfect squares, yes. So I'm going to factor this. Actually, let me move this over a little bit. Okay, so I'm going to factor this. And here's what happens, okay? In this first spot of each term, so in this first spot of each binomial is the square root of the first term. In this case, x squared. Okay, so the square root of x squared is x, so that goes there and there. And then this spot and this spot, so the second spot in each binomial is going to be this. Do this one while I have that, and then go back to here. The second one in each binomial is the square root of the second term. So in this case, it's 10. And then finally, I have my plus and my minus. Okay, so if I write this without all my little color coding here, I get x plus 10 and x minus 10. If I check these, or I should say when I check these, x times x is x squared, plus 10x minus 10x cancels out. 10 times negative 10 is negative 100. Okay, so let's follow that same process over here. And I'm going to use my little color coding. It might help us kind of see what we need to do. Okay, so I look first for GCFs. Okay, before I get ahead of myself here. I look for a GCF. There's no GCF other than 1. So 9 has factors of 1 and 9, 3 and 3. None of those go into 49. And this does not have an x, so there's nothing I can take out for GCF. So that means I need to factor it into two binomials because it's the difference of perfect squares. Okay, so let me back up for a second. I kind of skipped a step in my head there. So we look for a GCF. There isn't one. There are two terms. We say, is it the difference of perfect squares? Yes, it is. It's a difference. If I look at this first term, 9x squared, all parts of that term are perfect squares. And if I look at the second term, 49, all parts of that, just a number, is a perfect square. Okay, so my square root of 9x squared is going to go in the first spot, the square root of that whole thing. So the square root of this is going to be 3x. So 3x is going to go here and here because the square root of 9 is 3, the square root of x squared is x. Then I go to the second one. It's 49. The square root of 49 is going to go here and here. So square root of 49 is 7. 7 goes here and here, and then I have my plus and my minus. So all together, without all the coloring, I get 3x plus 7, 3x minus 7. Now if I check this again, you notice 3x times 3x gives me 9x squared. I have what seems sort of random in the middle. I have negative 21x and plus 21x. It doesn't matter that 21 doesn't show up anywhere else. It's just because it cancels out, right? So it doesn't matter. And then 7 times negative 7 is negative 49. Okay, let's look at the next one. We're going to do all 4 of these together, all 5 of these, because they're all a little bit different. So now I look at this. I always want to look for a GCF first, right? And if I didn't look for a GCF first, you'd kind of be stuck because 6 is not a perfect square, so you might think I can't really do anything with it. So my GCF here is going to be 6. Okay, if you check 6 is 1 and 6, 2 and 3, you kind of want to start with the biggest one and see if it's in 384. Rather than writing out all the factors, you can just see if 6 goes into 384, which it does. So I pull out the 6, and what I'm left with is x squared minus, if I take 384 and divide it by 6, I get 64. So I've done my first step. Okay, I didn't know what's going to happen next, and that's okay. I just pull out GCF. Now once I've pulled out a GCF, I look at what I have left, and I think, oh, x squared minus 64. Okay, there's 2 terms. Let me see if it's difference of perfect squares. So x squared is a perfect square, 64 is a perfect square. So I can go ahead and factor that. X squared, its square root goes here and here. 64, its square root goes here and here. A plus and a minus. So again, didn't necessarily look like we were going to get much out of it at first. Once we pulled the GCF out, now we have perfect squares. Okay, x to the 4th minus 81. Again, I look for a GCF first, nothing I can take out. The first term does not have a number other than 1, the second term does not have an x, so there's nothing in common. So I look, it has 2 terms, I see it's subtracted, is it perfect squares? Yes. This square root of x to the 4th is going to equal x squared, and the square root of 81 is going to equal 9. So they're both perfect squares. So I go ahead and factor it into x squared plus 9 times x squared minus 9. Now, we always have to look and see if we're done. And especially if there's more than 1, or if there's an exponent higher than 1, you kind of want to make sure that you're done. So x squared plus 9, we're going to talk in a minute about the fact that we just have to leave that alone. But if I look at x squared minus 9, hopefully this kind of sets off some alarm bells in your head, because this, again, is an example of difference of perfect squares. So I have to factor this one now. X squared is x and x, 9 is 3 and 3, plus and minus. So that took a couple of different steps to do. Now let's talk about this x squared plus 9. Can we factor x squared plus 9 or any sum of perfect squares? We've been talking about difference of perfect squares. So let's think about it. X squared plus 9, I mean, we kind of think about x and 3, right? Because those are the factor, or those are the perfects. I can't talk. Those are the square roots. All right, so x times x is x squared plus 3x plus 9. That would give us x squared, but it would give us plus 6x and a plus 9. So I got the plus 9, but that doesn't work because it has that middle one, right? What if I try x minus 3 times x minus 3? Well, then I get my x squared. I get minus 3, x, and then a plus 9 at the end. So again, I got my x squared and my plus 9, but these add up again. So I get x squared minus 6x plus 9. And then, what if I try one of each? Well, then I get my x squared. I get 2 terms that are going to cancel out, but I have a minus 9 instead of a plus 9. So that can't work, right? So if I want the plus 9 at the end, I have to have 2 numbers that have the same signs that I'm multiplying. But if they have the same signs, then in the middle, they're not going to cancel out. They're going to add together. So we can never factor the sum of perfect squares. Okay, now if you go on to Math 120, you'll be able to, in there, you'll talk about factoring the sum of perfect cubes and the difference of perfect cubes. And you'll be able to work with x squared plus 9 because there'll be something called imaginary numbers, okay? But we can't factor it in the real numbers. All right, so I am going to stop the video for now, okay? We talked about, let's just go back, we finished up those examples about solving easier or factoring easier trinomials. We did some that had a couple extra steps in them, and then we moved on to factoring the difference of perfect squares. The last video we'll do factoring by grouping, factoring harder trinomials, and then at the end I kind of have some strategies about what do you do, what are the steps so you know how to start. Okay. So we will end here and I will be back.